Okay, our next speaker needs no introduction. He's kind of the spark plug of this whole program. And Fabian's already introduced himself. So when Fabian's done, we'll have lunch. And we look forward to your presentation.
Bruce made sure that he mentioned lunch before my presentation, so I'll keep it short. Closer to me. Okay. All right. Very good. Can you hear me okay now? Great. Well, it's great to be here with you today. And I got a little ambitious as I put this presentation together, so I'll try to go through most of these, hopefully all of these, but time is always my enemy when I am presenting because I just have a lot of stuff that I want to share with you. So, and some of this presentation today will be a little bit on the philosophical side. There will be data for sure, but I don't want you to necessarily focus on the specifics of the data. I want you to focus more on the message of what I'm trying to present today. Um, we talk a lot about the 4 R's, the right, rate, source, placement, timing. Um, and I'll talk a little bit about that. But I think that sometimes when we talk about these things, we kind of give the false impression that this is simple. And judged by my receding hairline and my wrinkles, I can tell you that it is not simple. It's pretty complicated. And I spend a lot of time trying to figure some of these things out. And so today, what I'm going to do is share with you some of the challenges that I am seeing as I try to find easy answers, easy solutions, or at least some answers to help us manage nitrogen better. So to begin with, this is something that we did a number of years ago. We went into a field. Some of these are in metric, but it doesn't really matter. So about 100 feet long transect across the field, and we took soil samples every 6 inches in the foot depth and measured nitrate and ammonium in each one of these samples. And what you see here is the total inorganic nitrogen plotted across that transect for both corn or soybean in both a drain and an undrained field. And you can see the variability there. Even within 6 inches of one sample to the next, there is quite a bit of variability. And that variability tends to increase when we have undrained soils. So just keep that in mind. The other thing that we did with this study was to figure out, okay, how many samples do we need to collect in a composite in order to have some assurance that the measurement that we are making is relevant and adequate for that field. And we determined that it takes about 20 samples in a composite to have good information. So a 10% error margin and a 95% probability level. So nobody's going to be excited about collecting 20 samples. We normally do 5 and we feel like we are doing pretty good, but the reality is that there is a lot of variability out there and it's challenging. This is a more recent study. You heard Emerson talking about this a couple of years ago, I think. We did this study across, collected information from a lot of different studies that have been done in Minnesota. In this particular database, we have 34 fields, and we look at the precise nitrate test as a way to manage nitrogen. So if we go in season around, V3, V4, early season, take soil samples, determine how much nitrogen is in the soil, and determine how much nitrogen we need to apply. And if you look in here, you can see that we got to, 20 parts per million is where that tipping point is. But you can see the scatter here of all those, all the data that went into that. And so while we can say that it is 20 parts per million, you can see that there is a big cloud around that 20 parts per million. And so the PSNT is a useful tool. It can help us determine if we have adequate amounts of nitrogen in the soil or if we need more nitrogen. But it is not a perfect tool. The other thing that we determine out of that data is that in general, for all the soils that we looked at, we started the season with about 20 pounds of nitrogen or 5 parts per million in these particular studies. And these were all fields that did not receive nitrogen in the fall. They were all spring applications. And then out of that, we determined that if you need to increase nitrogen, let's say that you're below that 20 part per million, you need about 12 pounds of nitrogen to increase the ppms in the soil by 1. Okay, and so all of these things can help us manage nitrogen, but the important thing is that they are not perfect. When I was an undergrad, somebody told me, well, your science is not an exact science. And I kind of took offense of that. But the years and the data has humbled me quite a bit. And I think that that person was right. This is not an exact science. There are a lot of things that we do to manage nitrogen, but we need to understand that a number is not an absolute number, but it's a representation of what is out there. We talked quite a bit about soil nitrogen in terms of the ability of the soil to produce nitrogen. We are extremely fortunate in Minnesota to have very productive soils with high organic matter, and that's a huge benefit. We also know that when you look at soil nitrogen, this is a measurement of potential mineralizable nitrogen under ideal conditions. We know that when you have more organic matter, you have more potential and better amounts of nitrogen for that crop. And that is symbolized here by a whole bunch of soils that we collected across the state. You can see a nice linear relationship that as you increase the amount of organic matter, you increase the amount of potential mineralizable nitrogen that you have. But the thing that is interesting here is that you look at the database and then you realize that, okay, what is the difference between that point and this point, or any of the other ones that I kind of highlighted in there? They were pretty much the same kind of soil, same amount of organic matter, and yet substantially different potential for mineralization. And this is under ideal conditions. And so that is a big challenge right there. What are we not measuring? Because obviously there are some differences. I mean, they're producing different amounts of nitrogen, substantially different amounts of nitrogen. What is the difference? What are we not measuring? And those are the type of things that I think about as a scientist. My kids think that I'm boring because I think about these kinds of things, but that's the type of stuff I think about. What are we not measuring that we should be measuring to understand these things better so that we have a better way to predict how much nitrogen will be available? Another thing, this is from a study we did a few years back, looking at nitrogen 15. So this is an isotope of nitrogen, which allows us basically to trace where that nitrogen is coming from. When we measure nitrogen in the soil, typical methods, we don't know where that nitrogen came from. We don't know if it came from the fertilizer, if it came from organic matter, if it came from deposition from the atmosphere. We just don't know. When you apply this isotope, it allows you to track where that nitrogen came from, if it's from the fertilizer or something else. And so what you're seeing here is a whole bunch of different nitrogen rates that we had. And the two colors here represent the total inorganic nitrogen and the organic or fixed nitrogen from the soil. And so when you look at the fertilizer-derived nitrogen, it's just basically looking at just that. How much of the total nitrogen that was measured in the soil was derived from the fertilizer that was either in inorganic form when we measured it, or that was already in the non-available plant form, either fixed in the soil or in the organic form. And you can see here that we apply nitrogen, and then we went a few days later, about a week later, to measure how much of that nitrogen that we apply was in the inorganic form versus not plant available. And you can see that the majority of that nitrogen, 85% of that nitrogen, was not in the inorganic form, ammonium or nitrate. It was in some other way that the plant would not have access to unless it becomes mineral again. And then you look at across the season V8, R1 post-harvest, you can see that those numbers get even smaller. And then we went even the next year because this is a very stable isotope. You can measure it year after year. We went the next year at pre-plant and then post-harvest to see how much of that nitrogen that we apply in the fertilizer was still plant available, and it was pretty much none. It's like 1% of that total nitrogen was still in the inorganic form. Most of that was in the inorganic form or fixed in the soil. Another way to look at this is to look at, well, the plant and seeing how much of the nitrogen that actually ended up in the plant came from the fertilizer versus nitrogen that was not part of that fertilizer, okay? So we are not able to distinguish whether the fertilizer that we apply became inorganic or became organic and then went back to inorganic and the plant actually ended up taking it. We are just saying, okay, of the total nitrogen that is in the plant, how much of that total came from the fertilizer that we applied? And you can see those values right here. This is fertilizer-derived nitrogen versus soil-derived nitrogen, okay? And you can see that early in the season, V8, there is a good proportion of nitrogen in the plant that came from the fertilizer. The farther away we get from that point of application, time of application, the more nitrogen that came from the soil that was not from that fertilizer that we applied, okay? And that's the important point, that mineralization is huge. It contributes most of the nitrogen. In fact, I've done many studies, even with just regular fertilizers that we are not able to look at the label. And by any time after V8, there's hardly any nitrogen in the soil. If you measure how much inorganic nitrogen is in the soil, it's very little. Why? Because the plant has taken up everything that is there and now is depending on the soil to supply that nitrogen. And I've shown this slide before. This is from the database that we have for the nitrogen rate calculator. And we have different rotations here: continuous corn, soybean, 2 years of corn followed by soybean. And what you're seeing here is the yield that we obtain at the check plot with no nitrogen applied, okay? And so if you look at that, we go anywhere from 50 bushels to over 200 bushels of corn produced with no nitrogen across the database, across the state of Minnesota. If you do an average, it's about 116 bushels that we produce with no nitrogen on average in the state. That nitrogen is coming from somewhere, is mineralization mostly. And then if you do kind of a back of the envelope calculation on how much nitrogen you need to produce a bushel of yield, you can kind of estimate how much nitrogen we are getting through mineralization. So anywhere from about 60 to over 200 pounds of nitrogen are mineralized every year for a crop. So that also creates this challenge, and some of that is related to mineralization, some of this is related to just growing season conditions. This is a study where we are looking in blue at the optimum nitrogen rate and in red at the grain yield at that optimum. And you can see that the dotted line and the solid green line shows the mean yield and the mean nitrogen needed to get to that optimum. But you can see that there are years where it takes about the same amount of nitrogen to produce substantially different yields, and there are years where you need substantially different amounts of nitrogen to produce about the same yield, okay? And so those are the complexities that we are dealing with when we are managing nitrogen. So to say that we need to apply the right rate sounds very simple, and yet it's extremely difficult because there are so many complicating factors. This is a study that is ongoing. It's a long-term nitrogen study that we have across the state. And most locations we have corn and soybean or continuous corn or corn-soybean rotations. And basically what we have is a repeated rate study. And so what you can see here is we have different plots with different nitrogen rates. And within each one of those, you can pick up in this continuous corn side here, the check plots, across the field. We have basically 6 repeats of that rate that allows us to replicate those 6 repeats 4 times, do all the statistics for that. So we end up with 6 response curves where we can calculate the economic optimum within those 2 acres of land that this study takes. And just visually, you can even see some of those differences in here. You can look at the check plots. This is Rep 1, Rep 2, Rep 3, Rep 4. Even visually, you can see that they are not all alike. You can even start picking up some of the lower rates in some of the reps and not in others. Anyway, we use this information here. We collected all that information, then we are able to determine what the economic optimum is. Basically 6 response curves replicated 4 times each out of those 2 acres. And these are the results. So this was done over a 2-year period. So we have 12 site years of data across Minnesota looking at that question. And on average, the EONR, the economic optimum end rate, vary by 47 pounds within 2 acres. Okay? Now, if you extrapolate this to 180 acres or a bigger field, and Brad mentioned some of these things today of the challenges of, having bigger strips. Well, the bigger the field, the bigger the variability you're likely going to encounter. And so, if in 2 acres we can be certain plus minus about 20, 30 pounds, that's as good as it gets, my friends. I mean, I wish it would be better, It sounds kind of like, uh, you know, um, just flipping in a way. It's like, well, do whatever you want, I guess. Well, we are looking at data, we are measuring these things, we are really paying attention to what we are doing, and the best that we can come up with is, in the range around that economic optimum, the average, anywhere from 27 to 19 pounds, around that. So if we are doing 30 pounds within that economic optimum, I think we are doing pretty well, okay? Now, this brings me to what do we do? I mean, we talk about all these variabilities and all these things. What can we do? This is screen captures from the nitrogen rate calculator, the MRTN calculator, okay? It is a tool. It's not a perfect tool. And the reason it's not perfect is because we're dealing with all of this variability and some other stuff that we haven't even talked about that creates challenges. So this is out of the MRTN calculator where we use the price of corn and the cost of nitrogen with the agronomic responses to determine what that economic optimum end rate would be. And so if you look at this is for corn after soybean, our database currently has 165 site years of data. You can see what the economic optimum is 142, and then we put a plus minus $1 around that as a range. You can see what that is. And that's kind of where you are at. Now, if you look at the percent of maximum yield, you can see that within that, you're pretty close to 100%. You're not 100% because to produce that last increase in a bushel of yield, it takes more nitrogen than is economical, okay? Then you have this frequency diagram here that shows basically the percent of sites out of that database of 165 site years in basically 25-pound increments across the horizontal axis. And you can see the frequency that we have where the economic optimum was that number, okay, or that in that range. And you can see that, if you are applying the economic optimum as an average, you are typically doing very well. The other thing that is interesting is that once we pass that, there is actually, in the corn soybean, there are not that many sites that will yield better or will have that economic optimum in a much higher level than, this 142 to 155 range. If you look at the continuous corn, it's actually shifted a little bit to the right, but you can kind of get the idea that there is a distribution in all of these things. And so while it's not perfect, if you had to take the chance, and that's what we are doing here, is I will go for something that shows me as much data as possible to say, okay, it is very likely that you'll be okay or you'll be right or close to right if you're at that rate, and you can see that distribution. Now, if you feel that you need more nitrogen or less nitrogen, like Brad mentioned today, do your own studies. And as I showed you earlier, in that same plot of land, we have variability, and within or between years, you have variabilities. And so just to do a study for 1 year and to say, okay, I need more nitrogen or less nitrogen, you will know it for sure for that year, but you will not be able to really use that completely with 100% confidence for the following year. So you have to do this over years to start getting some confidence. Now, all of these may feel like, well, just throw the hat and do whatever. It's like, there is so much variability there. The interesting thing with all of these is that it actually works, okay? Sure, it doesn't work necessarily on every situation in every year, but in general, it works. And so this is the theory that we talk about. We have nitrogen rate, corn yield, we get an increase in yield to a point, that economic optimum that we've been talking about. Passing that point, you're not going to increase yield substantially. You may increase it a couple of bushels, but again, it's not economical. And then when you look at nitrogen loss, typically nitrogen loss is pretty low to about that economic optimum. And then after that is where we start to really see a huge increase in nitrogen loss. And in reality, we see that pretty often as well, and it works. And so that gives me confidence that even though our tools are not perfect and our values are not exact, they allow us to manage nitrogen within a good level of confidence that what we are doing is correct. This is actual data from the field where we have a nitrogen response to in corn yield to an optimum. In this case, it was 121 pounds. This was a corn-soybean rotation. We did this study over a number of years. And then you have here the residual nitrogen. And you can see that there is pretty low residuals. It's not zero, you know. We have about 70 pounds in this case of residual nitrogen at the economic optimum or below. But then is once we pass that economic optimum where we don't see a yield increase, that nitrogen, residual nitrogen in the soil starts to accumulate. And the challenge is that, of course, that nitrogen typically is not going to be there the next year. And you can see that in here with this green line. This is the same soil the next spring. We measure the amount of nitrogen in that soil. You can see that there was hardly any change in the amount of nitrogen between fall and spring when you are at or below that economic optimum. But once you go above that, that's where you start to get that separation, okay? So this is why I feel confident that that economic optimum is important environmentally as well as economically. It helps us on both fronts. If we are over-applying nitrogen, that's where we start to get into in double trouble. If we apply less than what we need, the trouble is not environmentally. We are not really helping the environment very much more than what we are if we are applying an economic optimum, but we are hurting our pocketbook. Once you go above that, it's a double whammy. You're hurting your pocketbook and you're hurting the environment. All right, and this is another study where we were again looking at the economic optimum equated to zero in here. And then we looked at the residual nitrogen in the fall and the spring, with the caveat that that data shows, you know, a substantial reduction. But look at those 3 or 4 red dots that are there. This was during one of those really dry years where we didn't really lose nitrogen. And so there are years where that residual nitrogen will be there, but oftentimes that's not the case. In fact, if those three dots weren't there, this would be kind of a complete flat line right here. Okay, so that gap will be even bigger. So there are situations where that happens, but we need to be looking at what is the probability, what is the chance that something will work. And I will tell you that residual nitrogen is not going to stick around for the next growing season for the most part, in most years. All right, let's talk a little bit about the right time. Now, this is again one where let's look at theory versus the reality. In theory, you look, and you've seen some of these graphs like this, where you look at the annual rainfall pattern and the potential for nitrogen loss, and they kind of follow each other, and the peak happens earlier before the peak uptake of nitrogen by the corn crop. And so rather than applying nitrogen here before this high potential for nitrogen loss, why don't we apply nitrogen here past this high peak, but before corn really starts to take up nitrogen? And that should work beautifully. And I would hope so. But yet, then you go to measure this in the field, and this was actually one of the first things I started when I started working here in Minnesota 11 years ago, looking at this very question. And I have a lot of data that shows something like this. This is just one of those examples, 49 site years of data. This was not just Minnesota, it was actually a larger study that included other states in the Midwest, where we looked at pre-plant versus single pre-plant versus the split application of nitrogen. For the reds, what we have is basically 40 pounds of nitrogen pre-plant, and then the rest at side rest around V8. For the yellows, we had 80 pounds of nitrogen pre-plant, and then the rest at side rest. And what we did is we looked at all of those treatments and say, okay, how many times out of all those 49 site years of data the split application produced the same yield as the single pre-plant application. How many times the split produced less yield than the single, or the other way around? And we looked at that data, and you can see that 80 to 84% of the time, it makes no difference whether you're pre-plant applying nitrogen or split applying nitrogen. And then when you look at these ones where you do see a difference, it's typically very specific conditions. Fields where you have extremely wet conditions that you lose quite a bit of nitrogen, those were the ones where the side dress application was better. Or very sandy soils where the split application is better. And so very specific conditions, but in large, we see no difference. And in fact, we looked at, in this study, we went back and we looked at all of the data that we collected there at total nitrogen uptake, and you can see these two lines that are together in here. 0 is the economic optimum, below 0 will be less than the economic optimum, above will be an over-application of nitrogen. And what you see is that between the split or the pre-plant treatment, we did not improve nitrogen use efficiency by the crop. The amount of nitrogen that the plant used was the same whether you were pre-plant applying nitrogen or split applying nitrogen. Those two lines are on top of each other. And then when we look at residual nitrogen after the growing season again, right here, 0 will be the economic optimum. We actually see that the split application had residual nitrogen that were higher than the pre-plant application. Interestingly, you know, I mentioned that range of about 30 pounds of nitrogen, that if we are doing around 30 pounds, it's actually, we are doing pretty well. Well, in this data set, we determined that about 30 pounds above that economic optimum, there is really no much difference between that pre-plant or split application or rates below that in terms of residual nitrogen. It's about the same. It's once we over-apply nitrogen by a substantial amount that we start to see some differences. And in this case, we saw that actually the split application ended up with more nitrogen at the end of the season than the pre-plant application. Now, based on utilization, it's not that the pre-plant did better, it's just simply we lost nitrogen earlier. With the split application, we just lost it later, but we lost it nonetheless. Another caveat with split applications and where they work or where they don't. This is a study where we had pre-plant treatments in red or split applications. And we had two conditions, drain or undrained field. Okay, this was a poorly drained soil that needed tile drainage. We have treatments with and without that tile drain. And so we have the economic optimum and the yield at the economic optimum. And I will run quickly here through several scenarios, and some of you have seen some of this data before. When we have adequate conditions in any growing season that is adequate, the drain versus undrain, it makes very little difference, and it also makes very little difference whether we were pre-plant applying or split applying nitrogen. Then we go into 2018 where it was a really wet year, and in that year, having adequate drainage was extremely important, and doing a split application was beneficial, especially if you didn't have adequate drainage. And then when we look at the total as an average across all of these different years, we find that drainage was extremely important in helping us manage nitrogen. We did better. We needed less nitrogen to produce more yield on average under drain conditions than the undrained system. And when we are talking about split applying nitrogen, a pre-plant application in general did very well if you have adequate drainage. It did not make much of a difference. The only time where we saw a benefit, or more consistent benefit across all of these, was under undrained conditions. You have more potential for nitrogen loss there, and so split applying nitrogen at that point was a benefit. And then we put all of these together. We saw that we compared drain versus undrained. We needed 28 pounds less nitrogen with drained soils to produce 7 bushels more yield. And as a total, in this graph, what we are looking at is the total nitrogen that we were able to account for in the plant soil system at the end of the season. We found that in the drained soil, we we were able to account for about 10 pounds more nitrogen than the undrained soil. So when you put all of that together, what you're seeing here is that when you have adequate drainage, you are going to lose nitrogen through leaching into the tile line. When you don't have adequate drainage, you are going to lose nitrogen, and you will lose more nitrogen, but you will lose it likely through denitrification. And if we look at those two things in a relative basis, we are losing more nitrogen in an undrained system than when we have a tile drain system, okay? Again, less nitrogen to produce more yield, and we have more nitrogen accounted for in that drain system. That's where we come up with that conclusion. And so, again, talking about the complexities is pollution swap, pick your poison. There are no easy answers. We are trying to figure out better ways to manage nitrogen, but there are no easy answers. If we have no drainage because we are concerned about nitrate leaching into tile lines that then end up in the Mississippi and down to the Gulf, potentially we are going to be losing more nitrogen to the atmosphere, which also has pretty important environmental consequences in terms of climate change. We are also likely going to have more phosphorus runoff because those fields will be saturated with water, and water will be running on the surface. Versus installing tile drainage, which, yes, we are going to lose more nitrogen through nitrate leaching, but we will produce better yields with less nitrogen. So again, it's one of these things where there are no easy answers, and you just have to figure out which one is the least difficult or the one that will give you the biggest benefit. Another thing, we continue to do work in this site where we have drain and undrained conditions. This is near Wells, Minnesota. This last year, we don't have the split application treatments now. So we have 3 nitrogen rates that you can see there, 0, 130, and 260. 130 being about the economic optimum under drain and undrained conditions. And this was last growing season where we had a lot of rain in June and even into July. And the interesting thing here, when you look at this significant interaction of drainage by nitrogen rate, is that if you look at the check plug with no nitrogen here under drain conditions, we produce almost as much yield as applying the economic optimum under undrained conditions. And so what this is saying here is that if nitrogen is not the limiting factor, throwing more nitrogen at a crop is not going to make a difference. It's not going to solve the problem. You have to be looking at what is causing this plant not to do so well, okay? In this year, and we did not measure roots or anything like that in this study, but I suspect very much that the undrained system did very poorly because most of that nitrogen was being denitrified, and the crop was having a really hard time getting established and having a good root system. All right, another study looking at the right source placement and time. We heard Kenny today talking about how climate is changing in Minnesota, and these changes are making it more difficult for us to manage nitrogen effectively. We could be doing everything right as far as we know with nitrogen management, and yet some of the changes and the difficulties that we are seeing with climate change on the weather that occurs on a growing season can completely erase those potential benefits that we try to accomplish with the management. This is a study where in Lamberton, where we have plots that have a perimeter around them, where the water from this plot will not go into any of the other plots, and the water from that plot drains into a specific well where we are able to measure the amount of water that went out and the concentrations of nitrate in that water so that we can calculate the load of nitrogen. We have 4 treatments only because it's a small plot. We are constrained by the number of treatments. So 4 treatments, 2 pre-plant at 180 pounds of either urea or ESN, and then 2 split applications where we apply either 60 pounds of nitrogen as urea or ESN pre-plant, and then we go around V6 and apply the rest of the nitrogen, 120 pounds, as agrotame because we are not incorporating it. So lots of data here. Again, I don't want you to focus necessarily on all the numbers. This is looking at the cumulative nitrate load for those 4 treatments, so urea, ESN, and then the split treatments. And you can see here that this is the loading. We also have precipitation. All of these little bars here represent the single rain events throughout the season. And what you see here is that treatments do make a difference. ESN, 100% ESN actually had the lowest load out of all those treatments. The other 3 treatments had about the same amount of load. The other thing that is interesting is that regardless of what source of nitrogen we were looking at, when you lost nitrogen for one, you lost nitrogen for all of them. What changed was the amount that you were losing, but all of them kind of follow the same pattern. And if you look at these bars, it tells you basically when you have excess rain, that's where you're going to lose nitrogen. And in this particular year, as an example, I kind of marked five places where we had the most loss, okay? And that's very typical. In most growing seasons, anywhere from 3 to 5, maybe 6 events, that's typically where we lose most of our nitrogen. It's not a constant throughout the season. It's just when we have excess precipitation. And again, with climate change, that's one of the things that we are seeing more challenging is that these high precipitation events, the frequency is increasing. Not only the frequency, but also the intensity. We get more rain in a shorter period of time than we used to, and that creates a challenge. The other thing that you can see across here is I kind of put what is typical in a growing season where we lose quite a bit of nitrogen typically early in the season because it's wet and we don't have a crop to take up water yet, and the soils typically tend to be saturated or close to saturation at that point, so any additional water will push water and nitrate in the profile. Then we go to this phase where we have rapid growth of the crop and it's warm, and typically we don't get as much rain, but even if we get rain, because the soil is dry and the plant is taking up a lot of water and nitrogen, we don't have a lot of potential for nitrogen loss, so this tends to be flat. And then later in the fall, when the plant is not taking water anymore, we have a grace period where the precipitation starts coming and replenishing water into the soil, but the soil is dry, so it's able to capture that water and retain it to a certain point. And then when we have, again, a lot of rain followed by previous rain that was not used, it was just been replenishing the water in the soil, eventually we start to get some nitrogen loss again because the soil no longer can retain more of that water. This is from a different study, but it shows really clearly the effect of drainage on nitrogen loss. These are different nitrogen rates. This black line here shows the cumulative drainage in inches, and you can see that the loss followed that line perfectly. So more water means more nitrate leaching. And again, when we are trying to improve what we do in management to reduce the environmental impact of agriculture, I feel that sometimes we are working with a moving target. We can be doing everything correctly as far as we can, and yet some of these large rain events that we are seeing and experiencing more and more frequently can kind of erase some of that benefit. Looking at ammonia volatilization now, in this study at Lamberton, so 2 years, 2 different stories. We have, again, the 4 treatments. The first year, you can see urea pre-plant. You know, as soon as we apply nitrogen, it starts to volatilize. We lose some of that nitrogen, then it plateaus. These arrows here show when we apply nitrogen pre-plant, and then for the split application treatments where we applied it. And so you can see that for pre-plant urea, pre-plant ESN was pretty low through the whole period. And then these are the split treatments where we didn't have very much nitrogen early on, fairly low loss. And then we split apply, the split application where we apply 120 pounds of nitrogen, and you see this huge increase in volatilization loss. Now, what happened in 2019 is that soon after that application, we got a little bit of rain, 0.3 of an inch of rain that helped just to solubilize that urea enough into the soil for it to create perfect conditions for volatilization, and you see that. 2020, same treatment, okay? We are using best management practices here, folks. We are trying to split apply nitrogen, do everything the best we can. The only difference was what happened after that application. After the application right here, we got almost 0.8 of an inch of rain. that move nitrogen deep enough into the profile that we did not see those volatilization losses. And so, again, ESN performed very well. Urea behaved fairly similar to the previous year in terms of their response. And then these split treatments didn't lose as much, simply because of the rain. It had nothing to do with management, okay? It had to do everything with what happened after that application when the rain came. And we know that from other studies, and Swetov shows some data on these, that you need about half an inch of rain to incorporate nitrogen deep enough into the profile that you will reduce the amount of volatilization loss. And then nitrous oxide, another way of losing nitrogen. So 3 years, 3 stories. 2018, here we have again the 4 treatments, ESM pre-plant, the dark green is urea pre-plant, and then these are the split treatments. 2018, we had a year where we had high potential for nitrous oxide emissions early in the spring and then also after the split application. Okay, so at both times we kind of had really wet conditions, higher potential for these to happen, for nitrous oxide to be emitted. 2019, we had really wet conditions early on, so the pre-plant treatment had the more potential for nitrogen loss, and we certainly saw that with urea pre-plant, not so much with ESN. You know, ESN did a nice job of protecting nitrogen, but then at side dress time, we had pretty low potential for these, you know, wet conditions that create ideal situations for nitrous oxide, and so there was really no much difference in there. And then 2020 was a nice year. We didn't really have much potential for volatilization, for these denitrification and, you know, nitrous oxide emissions, either pre-plant or side dress, and so you see that overall they were lower. Okay, so again, the management didn't change, but what changed is what happened after that nitrogen application in terms of precipitation. And so that is the big challenge. Now, that's not to say that we should not try to do the best we can with management, because there are differences. And here is a graph basically compositing or putting together all the nitrate, nitrous oxide, and ammonia emissions all in one graph. And you can see that in this case, ESN as a pre-plant application was the best performing one. I mean, it reduced losses, those total losses that we were looking at, by about 50% compared to pre-plant urea. So that's pretty substantial. Now, an important thing to realize too is that if we say, okay, this is a best management practice, this is great, it's reducing nitrate loss or nitrogen loss, all of these different nitrogen losses, by 50%, still not zero, okay? This is not zero. And I think that that is also an important thing that we need to realize and come to grips with. That as we try to improve things for the environment, our impact can be reduced, but it will not be zero, and we need to understand that. And other groups that are not in agriculture need to understand that as well. We talk about split applying nitrogen as a best management practice. We talked quite a bit about the fact that it doesn't always work. And in terms of environmental loss for this particular study, was that really a best management practice compared to the bad pre-plant urea treatment? You know, this is kind of the standard, you know, business as usual practice. Well, no, we lost pretty much the same amount, even though we were applying best management practices, okay? Because again, it has to do with what happened after that split application. And in this study, by happenstance, a lot of those years, we got quite a bit of rain and we got nitrogen loss. Now, if we look at the yield for these 4 treatments, you can see the high performers and the low performers. The split applications did very well, and so did ESN as a pre-plant application. The low performing one was urea, and we saw partly why. You know, we did lose more nitrogen through urea. I think with those split applications, while we did lose about the same amount of nitrogen total, I think, as I showed earlier with that M15 study, when you apply nitrogen, it does get immobilized quickly. But if you have already a crop that is taking up nitrogen aggressively at that point, you have more chance of getting some of that nitrogen into the plant. And so I think that's why we see these differences in yield here. And then the other big part, of course, is economics. And I think we need to talk about this because agriculture is a business and we need to be making money. I mean, we need to do everything we can to protect the environment, but ultimately, we also need to be profitable. And here I put the cost of these different four treatments, okay? So urea pre-plant was the cheapest, 100% ESM pre-plant was the most expensive one per acre, and the split treatments right here. And then this is the net return versus urea. So even with the highest, most expensive treatment of 100% ESM, we came ahead in terms of net returns compared to urea with 100% ESN. And of course, that went up as we did the split treatments using these prices. And so we need to recognize that perhaps we can do very well for the environment and still be profitable, okay? Sure, 5 extra here versus 26 extra here is a big difference. And I'm not saying that the farmer should say, well, I'm going to just go for this one because it's better for the environment. But I think that if we are really intentional in protecting the environment, there should be ways to help incentivize farmers, maybe pay that difference and say, okay, you can you can use this practice. Yes, it's not as profitable as something else that you can do, but environmentally it's much more beneficial. So we will be willing to pay for that difference. And I think that that's what we need to be looking at in terms of solving some of these really difficult challenges that we have in here in trying to balance making sure that we are profitable as an industry and that we are also good stewards environmentally. Couple more slides, Bruce, and I'll be done. This is that same site. Now we are not doing the treatments I showed you earlier, but from what we learned from that study, we decided to do a nitrogen rate study. Just simple, good old-fashioned nitrogen rate study using 80 pounds of ESM pre-plant and then applying the rest of the nitrogen as side dress. And so these 4 response curves here to nitrogen are what you see from 2021 to 2024. The dots represent the economic optimum for those different years. 3 of those years were fairly dry, especially 21 and 22. 23 was a little bit better. 24 was extremely challenging, a lot of rain. And so you see those response curves. The other thing that we are doing in this study is having nitrogen rates. It allows us to do regression across all of these nitrogen rates, but we are continuing to measure nitrate leaching, nitrous oxide, and ammonia emissions. In the previous study, we only had 1 rate of nitrogen, so we could not do that. We could say, okay, which one of these treatments is better than something else? By having a nitrogen rate response here, it allows us to see for each pound of nitrogen that you apply, how much yield you get and how much nitrogen you lose. And that's what you're seeing in here. This is just 1 year of data in 2023. All 4 years kind of show the same pattern. And so for simplicity, I'm just showing this one. Actually, 2024, we are still working on that data, so I don't have it. I'm really looking forward to looking at it because it was a very challenging year in terms of nitrogen loss. But you can see that in black, you see the nitrogen rate response, the economic optimum end rate, and then that flat line after that where we are not increasing yield by increasing nitrogen. And then these red lines show the nitrogen loss either through nitrate, through ammonia, or through nitrous oxide. And you can see that for both nitrate and nitrous oxide, as you increase nitrogen, the amount of loss increases linearly, okay? For ammonia, it made no difference. It's just a flat line across all the nitrogen rates. And then I put together as an average across all of the years, 21 to 23. Again, I'm still working on the 24 data. And you can see now what happens to nitrogen or to corn with nitrogen. It increases to a certain point. And then you have this regression here across the total nitrogen loss. This is composite across all those 3 loss mechanisms. And now with this kind of data, you can say, okay, if I am doing everything right, and again, the treatments that we chose in here are using the best possible management practices. And with nitrogen, now we can say, okay, if I am applying the economic optimum, this is where I'll be at in terms of nitrogen losses. If I go above that, what happens to my yield versus nitrogen loss. Okay, that's a bad situation. You don't want to go past that because, again, as I mentioned earlier, you're not going to increase yield. In fact, some of these years, because they were so dry, if you went and applied way too much nitrogen, you actually start to see a decline in the yield instead of just being plateau. And that, I think, has to do with water management. So the plant is evapotranspiring more water than it needs because you have a huge plant that is just using water ineffectively. But besides the point, not much benefit passing that point, but we do see this continuous increase in nitrogen loss. And so the other question could be, okay, we want to reduce nitrogen loss to the environment by X amount. With this kind of data, it can allow us to say, okay, if we want to go from this economic optimum at this point and reduce it by this much, this is going to be the yield difference that we will see, and this is how much it will cost. And so we can start putting some dollars, figures to these environmental benefits. All right, last slide, one of the last slides. um, this is across the 3 years, 21, 22, and 23, looking at nitrate, ammonia, and nitrous oxide losses, and the different nitrogen rates that we have in the study. The interesting thing that I want to point out of the data set here is that just because we are losing nitrogen one way doesn't mean that it will be the same for another way of losing nitrogen. And this gets illustrated very nicely here. 21 and 22 were dry years, so you can see nitrate leaching, hardly any nitrate leaching, okay? But then you look at ammonia and nitrous oxide, and those losses were substantially higher. 2023, we lose nitrogen through leaching, so there is very little nitrogen to be lost through denitrification, okay? So we are going to lose nitrogen, it's just how we're going to lose it. And this is what I tell folks, that we cannot have the cake and eat it too. It's like we are going to have some kind of loss. We may improve one thing and make something worse. And we need to figure out what those gives and takes are and figure out which one is more important. And then again, try to figure out better ways to improve it, but ultimately knowing that there will be some kind of nitrogen loss. There is a cost to food production, a cost to the environment, and we need to come to grips with that. And I'm not just talking about us here in this group that is mostly people that are dealing with agricultural practices, but also in terms of environmental protection and folks that want to do better environmentally, that are putting pressure into the agriculture industry. I think we all need to come to grips that there are things that we can do and we should do to improve things, but ultimately we need to come to an understanding that there will be a nitrogen loss and a cost to the environment. So final points, I think nitrogen-based management practices are extremely important. We need to continue to do research, and I'll go bald soon enough, and I'll continue to do work on that and lose more hair until I have no hair. But we need to continue to do these things to find better ways to manage nitrogen. We need to understand that the concepts and the theories that don't always pan out, and that's because of all of those variabilities and all those issues that I mentioned earlier in my presentation and many others that we did not discuss today. Ultimately, I think as we look to how to manage nitrogen, I think we need to use best management practices, expect nitrogen loss, and then figure out ways to manage that nitrogen loss. We heard Jeff Struck today talking about, for instance, about water recycling. Maybe that's one thing that we can do to, again, reuse some of that, because we are going to have nitrogen loss. If we can maybe recycle that, could be a way to minimize the environmental impact. We need to be creative. We need to continue to look for solutions like that. And then figuring out, okay, there is an environmental cost. How much is that? Are we willing to pay for that? And figuring that out. So after we do everything else that we can with the other 3 R's, to the best of our ability, I feel that the nitrogen rate is really the big one. All the other ones are, in a way, a little easier. Nitrogen rate is a challenging one because, again, hindsight vision is 2020. We know after we do a study how much nitrogen to the pound, how much nitrogen we needed. But the reality is that when we need to apply that application, we don't know what the growing season is going to do. And so targeting that economic optimum, and again, using the MRTN calculator is a really good tool to begin. Use that to determine how much nitrogen to apply. It will be the best situation. Why? Because you will be right more often than not, and you're not going to be over applying nitrogen in an excessive way that will create an environmental impact. So with that, I just would like to acknowledge I presented information from a whole bunch of studies. These are the graduate students in my program. I have a very dedicated field crew, very dedicated researchers that help me with the data. They make me look good, but all of this work is not me. It's a huge group of people and a lot of funding. And so I really appreciate all of these groups and all of these individuals to help me do the work that we are doing. With that, if there is time for questions, I can answer them. All right. All right. Oh, I'm in charge. That's dangerous, Bruce. All right. We'll answer a couple of these questions and then we'll go to lunch. All right. On the ammonia volatilization slide, the scale on the left side was only 4 to 5 pounds per acre. The scale makes it look really scary, bad, but it's actually very little. That is very true. And so I try as much as possible to, of course, maintain the same scale across things. But of course, when you have, 60 pounds versus 5 pounds, if you put that in the same scale, you hardly don't see anything. And it does not allow me to make some of the points I want to make. But it is true. It's not very much. Now, quantity is in the eye of the beholder, right? For the crop, 5 pounds is not very much. Agronomically, it makes absolutely no difference whether you lose those 5 pounds or not. Environmentally, though, it can be substantial. When we talk about nitrous oxide, same thing, you lose 3 or 4 pounds of nitrous oxide. It doesn't seem like that much, but nitrous oxide is 300 times more potent than CO2 in retaining heat in the atmosphere, so it is important. And the other part, too, is that some of these things are kind of surrogates for other nitrogen losses that we are now measuring. For instance, we look at nitrous oxide, maybe it's 4 or 5 pounds, but we don't know how much nitrogen, total nitrogen loss is happening with like N2 gas, which, it happens during denitrification. We would love for denitrification to always proceed all the way to reducing nitrogen all the way to N2 gas because it's not a problem. 78% of the atmosphere is nitrogen, N2 gas. The reality is that when we are losing 5 pounds of nitrous oxide, there are no very good estimates, but we know that at the same time that denitrification is happening, there is full denitrification, and that could be pretty substantial too. So that nitrogen is real nitrogen. So 5 pounds might represent 5 pounds of nitrous oxide, may represent, I don't know, this is just a guess, pulling it out of the hat. Maybe it's 20 or 30 or 40 pounds of nitrogen as N2 gas. And then it becomes important agronomically as well. So it's not trivial. Yeah. Let's see. Ammonia and nitrous oxide losses were similar in the study, but nitrous oxide represents just some of nitrogen gas loss under wet conditions. Any ability to extrapolate from nitrous oxide to total nitrogen gas loss? Okay, I just tried to answer that question, and I don't have a very good answer. Unfortunately, it's not like a one-to-one or any kind of relationship that we can just say, okay, for each pound of nitrous oxide that you're producing this much N2 gas. We just don't have that. There is not an easy way to do that. All right, last one. Thoughts on risk of fall apply N versus pre-plant apply N. It depends. How do you like that answer from an extensionist? So in general, though, I would say a fall application, you have much bigger chance of nitrogen loss than you would with a pre-plant application. And I have talked about some of these studies where we are comparing fall versus spring. And by and large, you have a higher potential for nitrogen loss. You will end up needing typically more nitrogen to produce lower yields with a fall application compared to a pre-plant spring application. And we can talk, whoever asked that question or the other questions that are here, we can talk afterwards, but I don't want to keep everybody from their lunch. Otherwise, I will not be a very appreciated person today. Thank you so much.